Okay, perfect. Yeah. So first of all, thank you so much, everyone, for joining in. Really appreciate joining in. We have great speakers following, and I'm here more than a speaker, but as a attendee to learn from other speakers. So today, what we are going to do is we are going to talk about scaling generative models at scale. And what I'm going to do is for next maybe 30 minutes or so is I'll run down by fine-tuning a stable diffusion model using Ray, right? So let's get started. And this presentation and the source code, GitHub, everything I'll share after this, and you will get an email as Jimmy mentioned. Okay, so before we get started, let's talk about Array, what it is and how we are going to use this when we do a fine tuning or in general any training. So Array is a cluster manager, or you can think of it as a distributed compute engine. And when we say compute engine, and that means there must be some infrastructure below. So you can have any cloud provider, AWS, GCP, Azure, etc., or in fact, you can run it on your local machine as well, or on-premise. And Ray sits on top of it. And then we have some specialized AI libraries which is built on top of Ray, which is the Ray core, and these libraries perform different tasks. So we have different libraries for training, inference, for RL, etc. For today's session, we are going to talk about Ray Train. Right? So this is the AI library, which is a wrapper on top of Ray core, which makes your training much smoother at scale. Okay, and you can use any framework of your choice, PyTorch, TensorFlow, etc. And you don't have to change that code much. You just have to add a few lines, and magically the code which runs on your laptop or one machine can scale to hundreds and thousands of machines. Yeah. So just for context, like GPT-2 was trained on Ray. A few of the largest model providers, they have post-trained on Ray. Canva does a lot of post-training, model training on Ray. And also they use this for their multimedia data processing. So let's pick an example of PyTorch and show you how this works, and then we will quickly jump into the Stable Diffusion. So let's say you have a PyTorch code, and the code that you have in PyTorch is not the code which you would run on your local machine, but let's say on multiple GPUs, maybe in one machine, but multiple GPUs. So the first thing that you need to do is you have to manually set up the group. So, and it would use NECL, so which is the a backend for NVIDIA-based GPUs. So you set up the group, and this group is now aware that this following training, I need to do it in a cluster of GPUs. And then the next step that you do is prepare your model. So let's say this line number 6, this is your model. This could be your diffusion model or any language model or any model of your choice. The first thing that you need to do is you need to use a wrapper to make this model distributed. So in this case, we are using DDP, but it can be FSDP or anything of your choice. And at this point, we are just talking about training. So it could be post-training or a pre-training, whatever. Right? I just want to show you how different it is when you introduce Ray, so that you can have that mental mapping, so that when we go to the Stable Diffusion code, you can connect these things. So our model is prepared now. Our setup is prepared. The next thing is we need to prepare the data loader, because now since the model is distributed, or I need to sample the data very carefully, because now a batch of, let's say, 400, I cannot have those 400 samples, same samples to be distributed in 4 machines. So I need to make sure that if I have 4 GPUs, out of those 400 samples, the first 100 should go to GPU 1, second 100 should go to GPU 2, and so on and so forth. So that's why we have to wrap this around with a distributed sampler. So that will take care of sampling your data in a distributed fashion. And once this is done, you can run the training code, and it moves every batch, or rather micro batch, to every GPU and starts the training. So that's about a pseudo code of vanilla PyTorch. Now let's see how array would change things here. So in this case, we are using PyTorch, so that's why we are importing array train.pytorch. And we just have to import two classes, two methods, prepare data and prepare data loader. Right? These are the two functions which are there. And what you have to do is you have to just take your model and just wrap it around with prepare model. So this will automatically prepare your model for distributed training. Similarly, you take your data loader and use this prepare data loader, and it will automatically make sure that your data gets distributed, no matter you use FSDP, DDP, etc., etc. It will be taken care. And see here, we are not using a distributed sampler, which you used here in line number 10. And the reason is array will automatically figure out that if there is only one GPU, then distributed sampler is not needed. But if it sees that in the cluster you have more than one GPU, then it will automatically attach distributed sampler under the hood. So these are this prepared data loader. If you see the source code, it's a wrapper on top of the PyTorch data loader. And once this is done, we prepared the model, we prepared the data, and this function we want to be executed in all the machines that the Ray cluster have. So how we do that? We stitch this function along with some scaling configuration, which contains how many workers that you want. Like here, we mentioned 16 workers and use GPU. That means 16 nodes it will have. It will run this training, and each node should have one GPU. Right? So, and you can give much more details in more granularity, but that's how you start the training. But what happens under the hood, right? So let's quickly look into that. So let's say this is your training function, which we saw. So this training function would be the function which contains your training code, and you want this code to be executed in all the workers, right? So before we start the training, we have scaling config, running config, checkpointing. So all these different configurations that you have to give. And this all combines ray train, right? All together. And this is exactly what I just mentioned a while back. And the first thing that you need to do is you import torch trainer, then scaling config, which contains how many workers that you want to run, whether you want to use GPU or not, etc., etc. And similarly, running config and checkpointing are different configuration that you want to give, because now that your training is happening at scale, you need to have some shared storage to save the checkpoints and all. So that shared storage could be S3 or an shared file system or whatever you feel like. And once this is done, you just tie all this together with torch trainer, right? And that is what we have seen. But the moment you run this trainer.fit, what happens is under the hood, based on your scaling configuration, it will create those many workers, and it will take your PyTorch code. And which PyTorch code it will take? It will take this training function, and it will copy it in all your workers. And now all these workers will work in parallel depending on what distributed strategy that you have used, whether you have used DDP, FSDP, or whatever. It will just take care of those synchronization. And that implementation should come from PyTorch or TensorFlow, whatever framework that you are using. So now let's talk about what we are going to do today with Stable Diffusion. So the previously, like whatever we discussed so far, it's kind of a primer of ray train. You can use it for fine tuning, pre-training, or whatever you feel like. And I will share you a GitHub repo which will have some code to get started to see how your transition would look like if you start with the vanilla PyTorch, then Ray with a DDP, with Ray with FSDP, and so on, so that you can connect the dots. So now, if you are aware of Stable Diffusion or GAN or any of these kind of generative models, you know that it has encoders. So basically a V encoder, which takes the image and it has some text, and you pass it through the encoder layer, and then you get the image in a smaller latent space. And then you also do the embedding of the text. And what you do basically is you next add some noise, and then you use a unit to denoise that, and then you just backdrop and minimize the loss so that it can generate. So let me now get back to my notebook and show you one quick example of how you can fine-tune a stable diffusion with ray train. Okay. Now the technique that we are going to use is we are going to use DreamBooth. This is one of the paper which came, I guess, in 2022. Which is on fine-tuning text-to-image diffusion model with a subject-driven generation. So what that means is basically, if you use a stable diffusion model today, the vanilla model, and you want to generate some image, it can certainly generate some image. But let's say you want to generate some image which is personalized. Let's say in this case, you see this. Let's say if you want to give a prompt that a dog sitting on the beach, you might get any random dog, right? So it may not be your dog, but let's say you want to generate the image with your dog, right? But it could be different things, like your dog sitting on the beach, your dog in a bucket, and so on and so forth. So that's what this DreamBooth fine-tuning technique is, which makes the fine-tuning very simple by just few samples. And what it does is basically it will use what we are going to do. We are going to fine tune. We'll add a LoRa layer at the end, and we will just fine tune that. And we are not going to change the model weights of the diffusion model, but we will just add an additional layer at the end, and we will just use few samples. And the way that we are going to use this is we are going to use a few of the libraries like diffuser, and then per for the LoRa fine-tuning. And that is what we are going to install first. So here we are just installing. And I'm running this on a Ray cluster. I'll just show you how you can create this. You don't have to pay anything, but you can just create a new account in any scale and you can get this. But you can very well run this in your cluster if you have any on any of the cloud providers. Okay, so first we install the required packages. And the second thing that we have to do is we have to prepare our data set. So since we are using this DreamBooth technique, so we don't need much samples. What we need is just need few samples of our object. So in this case, we are just taking a few images of our dog, let's say. And the way that this technique works with just smaller number of samples is you need to have a subject token that is something very unique. This should be the text which the Stable Diffusion might not have seen in their training process. Okay, so imagine that if this token is simply dog, then that doesn't distinguish between your dog and the dogs which were trained during the pre-training phase. So you can give some random string or very unique string here, and then you give some class like what it is basically, right? So you have to give something like, because this random string might mean dog, cat, whatever, but you just have to tell what the subject is, and that's all. So this is the place where I will be storing all my data set or the images. I'm just copying it there. And if you look at this images, it looks like this. And it is better when you do a fine-tuning stable diffusion using this technique. The image should be like, all the image should be ideally square dimension with same number of rows and same number of columns in terms of pixel. And if the object is in the middle, you get a better performance, right? So this is something that the papers tell you. So once you have these images, you just copy these images to the cloud. So this is what I'm doing. I'm just copying this image from my local system to the cloud. So in this case, it is an S3 bucket. And this would be accessed through all the worker nodes when we start the training. And you can just skip this part for now, but this is what we are going to use after the fine tuning. We will just see how our fine-tuned model is now performing. So when you do the prompt at the end of the fine tuning, you need to give that subject token and subject class so that the Stable Diffusion model understand that, okay, what you want. Right? So if I just say dog at a beach, I will still get the same image like before. But after fine tuning, we expect that it should be an image which would be similar to my object. In this case, my dog's image. So the prompt, we are just preparing this prompt, and we will be using it after the training is complete. So we are using, so the training code, as we saw earlier, the training code can be an PyTorch, TensorFlow, HuggingFace, whatever. It's up to you to use. So that is what we are using. So we are just using the training code, which the HuggingFace Accelerate engine or framework provides for this. And since that's a big code, and you can actually run that code through the terminal, but since we want to run it through here just to make it more visual, we are just importing it. And since it takes lots of command line argument, we are just parsing those arguments in a cleaner way. So we are saving all these command line arguments here with the pre-trained model. So this is my pre-trained model. And we are telling our subject image path, that is the cloud S3 bucket, where we have uploaded all those images of our dog, and a few of the other pre-training configuration hyperparameters. Okay. Once this is done, we are saving all these arguments in the training arcs. And now we are going to use array-train for training. So for that, first we need to specify a model checkpoint, because this training might fail, hardware fails, and all of that. The cluster will restart. The cluster will resume the training, but you need to make sure that you have your checkpoint. So this is what we are storing the checkpoint. And then we just start the training. And the training is pretty straightforward. You can ignore this part. We are not using weights and bias API for monitoring, but you first initialize the array cluster, and you pass all the environment variables. And then this is your training function. Right? So this is just few lines, because we have wrapped the main code .main. We have just imported that. So this is the actual training function. So if you remember in this presentation, this was the training function that we used, right? This is the training function that we want all this worker to use, right? So here, that training function is this one, okay? And we are just parsing some arguments. And just like we have seen, we just call torch trainer. We send that function and the arguments that we have stored before, and the scaling configuration. So we are saying that run it on 4 workers with GPU. And we can actually mention which kind of GPU you want. So this is a wrapper function that we have created. It's a utility function. Just in case A10 is available, just take that. Right? So here you can directly mention what kind of accelerator that you want. Right? So A100, H100, whatever. So this is where you will mention that. And then you just do array.trainer.fit. So this might take some time. So we have executed this, and after all of the training, you will get the fine-tuned model. So let me scroll down. So now we got the fine-tuned model after the training is finished. Now we want to just send the prompt. And prompt we have already saved before, and the same training arguments. And we want to generate that, right? And that is what we are doing here. And how we are doing this, we are just importing Ray, and we are saying ray.get. And again, we have a utility function called generate. And if you see this utility function called generate, it actually takes the prompt and the model checkpoint, right? So this is the, if your model is trained, it will take the last model weights, and it will just append, it will just use it along with the pre-trained model. So if you see that pipeline, you have that Stable Diffusion pre-trained model along with your checkpoint. Okay. So once this is done, we can see how the model performed. And see this, this is your dog, and the prompt was dog on the beach. So now it is not generating any random dog image. It is using your dog's image and just generating these images as per your prompt. And the magic is happening because you are using the same subject token, right? So you might wonder that if you use the same prompt to the pre-trained model, how it would look. And when we tried to send to the base model, we got this kind of image, right? So there's still a dog, but it is not your dog. And what we have done is using LoRA and fine-tuning it with LoRA and DreamBooth, we were able to fine-tune this model, Stable Diffusion model, with just few samples in a distributed fashion. And we can customize and use it for our application. Okay, so that's all I have for today. I guess there are a few questions. What I will do is I'll go over them now as the second presenter presents, and I'll answer it. And I will share this GitHub repo, Ray for developers. You will see the distributed training folder. Inside that, you will find all these distributed training techniques and how you can get started. And I will also share the notebook, which I was sharing within this GitHub repo. So that's all from my side. I'll just